Hello and welcome to the first video of a series of videos where I'll be covering various data structures topics. Today's video will be covering trees, and we'll be talking about what makes something a tree, and then we'll be going into more detail about binary trees and tree traversals. So let's get started. What is a tree? A tree is a recursive definition, and all it says is that you have a node that has 0 or more trees as children of that node. And for something to be a child, we just draw a line like this. So let's add 3 children here, and we'll add a couple more nodes to make it look more like a tree. There we go. And so in this case here, we have a node that has 3 children as subtrees. This right here is a subtree, this right here is a subtree, and this right here is a subtree. And remember, this is a recursive definition, which means that inside of each of these boxes should be another tree. So if we look here, we have a node with 2 children, this is a node with 3 children, and this is a node with 0 children. And this is still considered a tree, because remember, a tree is just a node with 0 or more children. So it can still have 0 children and be considered a tree. All right, and so before we move on to other trees and like binary trees, let's talk about some key terminology. This right here is the root of the tree. It's the node in the tree that is at the top level, and it also has no ancestor nodes or parent nodes. So it's not a child of any other node. It is also considered a parent node because it has 3 children. Right here, 1, 2, and 3. So these are all children node right here. Of course, a child node can also be a parent node itself. For example, this one here is a parent node of 3 children. And this right here is a parent node of 2 children. You also may hear the terms internal nodes and leaf nodes. A leaf node is any node that has no children, and let's use blue to describe that. There we go. So right here, for example, is a leaf node. This is a leaf node. These right here are also all leaf nodes, like that. And an internal node is any node that isn't a leaf node, or any node that has at least one child. So for example, this right here is an internal node, and internal node. There we go. You also may hear the term the height of the tree. The height of the tree refers to, let me get the black marker again. This is the height of the tree right here. And in this case here, we have a tree of height 2. You may hear some places say that, oh, if you have a tree with one node, that's a height of 1. For this video, we'll be saying that if it only has one node, it's a height of 0. So this starts at height 0, height 1, and height 2. So this right here has a height of 2. All right, and so I think that is all the terminology we need to cover, so we can now move on to binary trees. All right, so what is a binary tree? A binary tree is a tree where every node has at most 2 children. So an example before, we had nodes with 3 children. That was not a binary tree. Now, the node can still have 0 or 1 child, but it can have at most 2 children, so it can't exceed more than 2 children. So let's draw one, for example. This right here would be an example of a binary tree. Now you may hear some terms like a full binary tree or a complete binary tree. A full binary tree simply states that it's a binary tree where every node except for the leaves has exactly 2 children. So in this case here, this is not a full binary tree because this right here, this node right here is not a leaf node, it's an internal node that only has 1 child. To make this one full, I'd have to add a child like that. Now a complete binary tree is a little different, and it basically states that every level of the binary tree except for the last is completely filled, and that all nodes are as far left as possible. So for example, this right here is a complete binary tree because the first level right here is completely filled. You can only have 1 node here. And this is the last level, so it's okay that it's not completely filled. And all the nodes are as far left as possible. Now with a tree like this, for example, this is not complete because while the first level is completely filled, the last level does not have all the nodes as far left as possible. Now let's draw a better example, one that isn't just 2 nodes. So for example, this one right here would be an example of a complete binary tree. We have the first 3 levels right here all completely filled, and then the last level. Now last level can be filled if you want it to be, but it doesn't have to be. And in the last level, all the nodes are as far left as possible. Now if I were to add a node here, this would no longer be complete because this node is not as far left as possible. You'll see complete binary trees being used in binary heaps, but we're not going to talk about that because that's outside of the scope of this video. All right, now let's talk about when you would see the use of binary trees. You'll see them being used in binary search trees, and that's most frequently where you'll be seeing them used. So let's talk about binary search trees then. All right, so a binary search tree is just a binary tree, but it has a specific ordering to the nodes. And so let's actually put some values inside of our nodes. And now frequently we'll be seeing them used with numbers, but we can put anything else in them if we really chose to. So let's add a node here, and this will be our root node. And let's just add a number in, let's say 50 in this root node right here. There we go. So let's say we want to add another node to our binary tree. Now, the rule for a binary search tree is that all nodes less than this node should go to the left, and all nodes greater than this node should go to the right. So if I wanted to add, say, 25 to this, right, I would compare it to this root node, and I would say, well, 25 is less than 50, so I'll put it in the left. And then the left tree is empty, so we'll just create a node right there. Now if I want to add 75, for example, it would go to the right of the 50. Right? Now let's say I want to add the number, let's say 40 to this binary search tree, right? So I go up here and I say, okay, is 40 less than 50 or greater than 50? Well, it's less than 50, so it goes to the left subtree. Now we can't just add a 40 here because that would overwrite the 25. So what we basically do is say, okay, well now we take 40 and we add it to the binary search tree here. Because remember, a tree is a recursive definition, and this right here is another tree. So we say, okay, let's add 40 to 25. We follow the same logic again, and we say, well, 40 is greater than 25, so we're going to the right. And now that we have an empty spot right here, then we can create 40. There we go. So no, let's try another one. Let's try, we want to add 60, right? So 60 is greater than 50. And we try inserting into this tree, and it says, well, 60 is less than 75, so 60 goes here, right? And if we notice, all values to the right of 50 are still greater than 50. So if I draw a dividing line here, right, we can see that anything ever inserted on this side will always be greater than 50. Anything less than 50 will be inserted on this side over here. Now, what about some duplicate values? A lot of times, with binary trees or binary search trees, we'll just say no duplicates allowed. But if you want to allow duplicates, you can just say, well, pick a side that we will say equal to, right? So right now, at the moment, it's on the right side, it's greater than, on the left side, it's less than, right? And we just pick one and say, okay, all equal values go on this side. So let's just say right side is greater than or equal to. So if I want to insert a 50, I would say 50 is equal to 50, so it goes on the right. It's less than 75, so it goes down to the left. And say it's less than 60, so we'll go down over here, right? And we notice it still keeps the rule of the binary search tree where every value here, this time it's not just greater than 50, but greater than or equal to 50. All right. So what would be the point of doing something like this? Well, it helps optimize search algorithms, right? So let's just say that, let me erase this because this isn't the best binary search tree. 60 and 80. So right now we have a complete and, 80, complete and full binary search tree. So let's say you're saying, okay, well, I have a list of numbers now, essentially a list, right? You can interpret this as a list, 12, 25, 30, 50, 60, 75, 80. And I say, okay, the 60 exists in this list. Now, normally, if I were to write out a list, so let's write this out real quick. Okay, can you check if 60 exists in this list? Well, you'd have to start at the very beginning and say, is this 60? No. Is this 60? No. Is this 60? And so on and so forth until you got to 60, right? So in a worst case scenario, what if 60 is at the end of your list and you just end up checking the entire list just to find out it's at the very end, right? Or in the worst case scenario, it's actually not even in the list at all, so you have to check the entire list before you find it. The binary search tree allows you to just eliminate certain parts of the list. So right here, I basically compared to 50 and I say, well, I don't even need to check anything on the left side here because 60 is greater than 50. So if I were to have a 60 in this tree, it would have to be on the right side, right? So that allows us to, in this case, eliminate up to half of the elements. So these don't even need to be checked anymore. So you don't have to do this part where you do 12, 25, 30. And when we get to 75, we can do the same thing again, right? So if there were a bunch of nodes, we can then say, okay, well, 60 is less than 75. So anything on the right side of 75, I can just completely ignore. So if there were 100 nodes on this side, I could just completely ignore that and then go over here and say, okay, there's my 60 and there and it exists, right? Now, what if I want to check if something doesn't exist? So let's go with 55, for example. Actually, let's go with 65. So I check 65 is greater than 50. So if it exists anywhere, it'd be in the right subtree. And then 65 is less than 75. So if it exists anywhere, it'd be in the left subtree of that. 65 is greater than 60, so I go on the right. And then when I get to the right, I notice, oh, I'm at an empty tree now. There's nothing here. So therefore, it cannot exist in the tree. Because if it did exist in the tree, it would have to be on the right of 60. So we could just return false. All right, so I just drew a bigger tree so we can see a better example of how this can help eliminate a lot of redundant searches. So normally, if you want to search through just a standard list and you want to see if a certain element exists, or if you want to see if a certain element doesn't exist, right? It takes O of n time because you have to start from the beginning of the list and work your way all the way through all n elements before you can determine the answer to your question. So normally, if you do linear search, it takes O of n time. Now with binary search, assume we have a balanced tree. Now I will explain what balanced tree is later, but if we assume we have a balanced tree, then I don't have to check all the elements, right? And at most, the deepest I can go is just the height of the tree. So then in that case, it depends, okay, well, what's the height of the tree then? Well, if we notice that every stage we split the tree into two, right? So we have 2 here, 2 here, 2 here, 2 here. So we have a total of n elements. Then what ends up happening is this actually has height of log n. in a balanced tree at least. This is the best case scenario, it has a height of log n. If it's not balanced, then it won't have a height of log n. But if it's a balanced tree, it will have a height of log n, which means that I will never have to check, for example, if I go down the right side, I don't have to check the left side. Really at the end of the day, I'm only checking one node per level, right? So if I check the 50, then I would check, let's say I'm looking for 65, right? I check the 50, then the 75 on the next level, and then the 60 on the next level, and I only check one node per level. So in other words, the amount of checks I have to do is just equal to how many levels I have to go through. And if you have log n levels, then we have a BST search time complexity of O of log n. And this can help reduce the time complexity for searching very, very quickly. All right, so let's talk about the time complexity about this binary search tree, because I mentioned balanced just a moment ago. Right? So what makes a binary search tree balanced? Well, visually, a binary search tree looks balanced if roughly the left side and the right side are about the same height, right? So, something like this looks balanced, right? It doesn't look all one side, or it's not tilted on the other side, whereas perhaps something like this wouldn't be so balanced. It feels like it's really right heavy, right? Now, formally, the definition of balance basically means that as long as the left subtree and the right subtree have a height difference of at most 1, and the left subtree and the right subtree both have to be considered balanced, then the tree is considered balanced, right? Now notice there are two conditions. Number one, the difference in height. So if I say difference in height of left and right has to be less than or equal to 1. Specifically the magnitude, right? So we're not going to count negatives, just assume that the magnitude of the difference is less than or equal to 1. And, this is important, both left and right are also balanced. Right are balanced. There we go. So why is this important? Well, for example, now actually let's talk about what's the worst case in a tree that isn't balanced, right? So let's say I want to do binary search, but let's say I have a tree that looks like this. Let's erase this tree here. There we go. So yeah, let's say we have a tree that looks like that, right? Well, what ends up happening to time complexity is, well, you have to check this node, then this node, because you have to check one node per level, right? So we check this one, then this one, this one, this one. If the tree looks like this, then basically the height of the tree is just equal to the number of elements, or number of elements minus 1, technically. So that means that the time complexity of this is no longer log of n, it becomes O of n, just basically linear search, right? Because this tree doesn't allow you to get rid of half of the elements at every step, because there's no half, there's no left side, it's all right heavy. So this isn't considered balanced, and this would be very bad for searching. So then why is this number two condition here so important? Well, if I have a tree that looks like this, let's say half the elements here are like that, and then the other half are here. Well, if I were to only view the number one step, or the number one condition, based on this, the height of this tree is 0, 1, 2, 3, 3, and the height of this subtree is 0, 1, 2, 3. So the difference in height is actually equal. Or there is no difference of height, rather. So if I didn't have condition 2, then this would be considered balanced. But we all know that if I were to try to search for something, this barely does any elimination. It does one step of elimination, and then it goes on to the rest of the tree, and it doesn't do any more elimination based on that. And the time complexity then becomes O of n again. So that's why it's important that both the left and right also have to be balanced. So if you're checking the balance of a tree, it's recursive, right? You have to say, is the difference between the left and right, or is the magnitude of difference between the left and right subtree less than or equal to 1, or difference in height? And you have to then check that the left is balanced, and then also that the right is balanced. All right, so let's talk a little about the height of the tree being log of n. I kind of skimmed over that just a moment ago, so let's actually talk a bit more about that. So let's draw a full binary tree. Remember, a full binary tree means that every node except for leaf nodes has exactly 2 children. And let's actually make it complete too while we're at it. There we go. Okay, so if with this binary tree, because it is full, now this is only a property of full binary trees, and you will notice that the number of internal nodes, or number of leaf nodes, is equal to the number of internal nodes. I'll just abbreviate that with int nodes plus 1. Now, I'm not going to go on an induction proof for this. You guys can try to figure it out yourself, and I may make a video on it later on, but for the time being, we'll just assume this to be true. Okay, so if this is the case, then that means that, and remember that every node in a tree is either an internal node or a leaf node. So let's say the leaf node, there's L, leaf nodes, and then there's I internal nodes. Well, then the total number of nodes n is equal to L plus I. And since the number of leaf nodes is really just 1 greater than internal nodes, then really you can say that the number of leaf nodes is essentially n divided by 2. And the number of internal nodes is n divided by 2 as well, right? Technically, this is a floor, ceiling, but basically speaking, they're half, right? So half of them are leaf nodes and half of them are internal nodes. Now you may notice that at every level, right, if you have this many nodes here on this level, then the next level has half that many, right? Because we have 1, 2, 3, 4, 5, 6, 7, 8, and then there's 4 nodes here. It's because every node has 2 children exactly. So in that case, if we wanted to see how many parents are, you just divide by 2, right? So if you have n over 2 nodes here, then there's n over 4 here, right? And then there's n over 8 over here, and then there's n over 16 here. And basically, you're trying to see how many times you can divide it by 2, right? Until you get to the very top, when there's only 1 node left, you basically just keep dividing by 2 until you can't anymore. Now, in other words, I basically ask, if you're saying how many times can I divide a number by 2 before I hit 1, you're basically saying 2 to what power equals that number, right? So basically saying that 2 to the height of the tree, right, because that's what this is equal to, oops, there we go, is equal to the number of nodes n. And then we can, if we want to figure that out, we can just say, well, log base 2 of n is equal to height then. And as I said earlier, if we're doing search, you're basically searching through the height of the tree. So if we're doing search on a balanced tree like this, then the search complexity is just log of n. So that is kind of basic intuition as to why on a complete, or not complete, but on a balanced binary tree, the search time complexity is just log of n. I actually forgot to mention this earlier, so I'm just inserting this into the video, but a lot of things will require a tree to be balanced because you don't want to deal with an unbalanced tree where you have to deal with O of n search. Now, there are actually trees that can self-balance themselves, meaning that, you know, as you insert, or maybe after a couple insertions, they'll just rebalance themselves. And, you know, these trees are called red-black trees. There's also AVL trees. I'm not going to cover them in this video. I'll probably make a video on AVL trees in the future, but I just wanted to let you guys know there are trees that can actually balance themselves and take care of the unbalanced issue. All right, so let's talk about traversals, which will be the last topic of this video. Traversals are very important with trees, and a lot of times you will actually have to deal with traversals. There are various different ways of implementing traversals, but in this particular video, we'll just be talking about what the traversals are. And I might make a video on how to actually do certain traversals later on. So let's actually draw up a tree real quick, and I probably should have done this beforehand. But let's come up with just a very simple tree that has a couple of nodes here. Okay, so this should do. All right. There are 3 different types of traversals. There is a in-order traversal, there's pre-order, and then there's post-order traversals. Yeah, there we go. An in-order traversal is left child, then the root, which I should probably, let's use, I didn't think of this because I don't want to use R for root because R can also stand for right. So what I'm going to do is I'm going to put a star for root because I can't think of anything else. And then right, a pre-order is the root first, there we go, then the left and then the right, and post-order is the left child and the right child and then the root. And as with all things trees, this is recursive. So if I want to do an in-order traversal of here, I'd have to do an in-order traversal of the left child and then put in the root and then an in-order traversal of the right child. Now, the easy way to remember these is, well, in order, just left, middle, right? Right, so left and then the root, which is always in the middle, and then the right child. Pre-order, basically pre and post refer to the position of the root. So pre means that the root should come before the left and right, and then post just says that the root should come after the left and right. I just realized there's a bit of glare, so you can't actually see this part, but it says left and right. Okay. Let's talk about then the specifics of the in-order. So in order to do an in-order traversal, all you have to do is say, I'm going to do an in-order traversal of the left. So these are all recursive. I'll write that again. Recursive. But I'm going to do an in-order traversal of the left. So if I want to do one here, so let's start at 15. I do an in-order traversal of the left child. So I do an in-order of this. And then I want to call in order of the left of this child, or this node right here. So this is the 5. And then I do a in-order traversal of the left of this, which happens to be nothing. So there's nothing to do. And then I print out 5. And then I do an in-order traversal of the right child, which this case here doesn't have a right child, so this just is done. And then because I finished the in-order traversal of this, that means I can now print out the root of that. So it would be up here. So now 5, 10. And then now that I finished this part, I have to call an in-order traversal of the right child of 10, which is 8. I call in order of the left child of this is empty. I write out 8. I call in order of the right child of 8. There's nothing there, so it's done. And now that I finished the in order of this, now I go back up to my original call. So up here, I write the 15 down. And now I do an in order traversal of the right child of 15. So I come here again, get to 25, call in order of the left. In order of the left of this is empty, so I go to 20. And then I call, and let's actually add a value here, just to show you something. There we go. So I call in order of the right, which is 22. There we go. So, you can have no left or you can have no right, and this still should work perfectly fine. So 22, and then now this is done. So now I can write down to 25. And then I call in order of its right child, which is 30, which then I call in order of its left child, which is nothing, so it's done. Then I write down 30. I call in order traversal of the right child of 30, and there's nothing again, so that's done. And now that this is done, that means that this entire thing is done, which means the whole thing is now done. Now in a binary search tree, you may notice that an in order traversal just results in a sorted list, right? Because you're always going left, middle, right, and then in a binary search tree, the left child is less than, root is in the middle, and the right is greater than. So you always have this sorted order. Now for pre-order, it's basically the same thing, just in a different order. So if I want to do pre-order of this tree again, I would first write down to 15 because it says root first. So 15 goes down. And then I call pre-order of the left, which means I write down the root of that first, which is 10. And then I call pre-order of the left here, so it's 5. And the 5 doesn't have a left and doesn't have a right, so it's done. And then I finish that, so I go to the right, which is 8. And I call pre-order of the left, nothing, pre-order of the right, nothing. So this is done. Now that this is done, I can now move on to the right. So the right child is the 25 first, because I write the root first. And then I call pre-order of its left child, which is 20. And I write down 20 first. And then I write the pre-order of the left child of 20, which is nothing. Then I call pre-order of the right child, which is 22. And then now that I finished this left, I can move on to the right, which is 30. And 30 doesn't have any children to work with. So the pre-order traversal of this would be 15, then 10, then 5, then 8, then 25, then 20, then 22, then 30. And post-order is, the same thing, except once again, we just put the root at the very end. So we call post-order of the left, and we call the post-order of that left. Post-order of this left is nothing. Post-order of right, nothing. Then we write on the 5. And then we say, okay, now that we finished this, now we can call the post-order on the right child of 10, which is 8. And it doesn't have a left or right, so that completes. And now we can write to 10. So we have 5, 8, and then 10, so left, right, root. And then now that this is done, I can now do the right child, because basically post-order I have to do the right child of 15 now. And so now I call post-order on this child, which is then calling on the left here. And then this has to be post-ordered as well. So I call the left, nothing there. Then I do the right, which is 22. And now that I finish the left and right of the 20, I can write down 20. Now that I finish the left of 25, I do the right of 25. So then there's post-order of 30. It doesn't have any children, so there we go. And then now I finish 30, I can do 25. And then now that I finish 25, I finish the left, I finish the right, so I can write 15. So the post-order would be like that. There we go. And if you do it recursively, it's actually fairly simple. And for these 3 different orders, it's just a rearranging of the 3 statements, essentially. You'll rename the functions, of course, because you want to change in order to pre-order. But outside of that, it's just a rearrangement of the different statement calls. So I think that'll be it for this video. We went over traversals, binary trees, and trees in general. I think that'll be it. So in the future, I'll be going maybe a bit more into some implementations of these right here. But for the time being, this will be it. Thank you for watching, and hopefully you guys learned something from this.